In this chapter, we're going to be investigating a process that is basically the inverse of differentiation. We're going to kind of undo derivatives in this chapter and investigate what that means, how to work problems, how that brings us greater power in our study of calculus in word problems and so forth. Let's begin with this idea. Suppose I have functions that I'll designate with an uppercase f of x and functions that I'll designate with a lowercase f of x. And you'll notice that if I take the derivative of x cubed, I get 3x squared. Now, what is the derivative of x to the fifth plus 4? Well, the derivative of x to the fifth is 5x to the fourth, and the constant goes out. The derivative of x to the fifth minus 7, the derivative of the x to the fifth is 5x to the fourth, and the constant goes out. Now, if I try to go in the other direction, if I'm talking about 5x to the fourth here as the derivative of something, then what kind of something does this look like? Well, let's see. We've had an experience here with x to the fifth giving as its derivative 5x to the fourth. So if we're going to go in the other direction, it kind of makes sense that 5x to the fourth will produce an antiderivative of x to the fifth, and then some constant. You see, these constants disappeared when we went in this direction. They need to make a reappearance when we go back in the other direction, and so we would say then that this is x to the fifth plus c. Now, c is a variable. It's a constant, but that constant value can vary from problem to problem. So when we take an antiderivative, or when we find an antiderivative function and we tack on this c, it means that we have really a family of functions that we're talking about. There isn't just one antiderivative function. It is many of them. Now, sometimes I'll misspeak and I'll say, let's find the antiderivative, but let's understand that when I put that c on there, we're really talking about a family of functions and not just a single function. Okay, these are called, I've been referring to these as antiderivatives, and these are the derivatives of those antiderivatives. So we want to be able to work in both directions now. A lot of times the derivative function is written in a derivative form, and when that function is written in that form, that is in this form, it's called a differential equation. Now, these are differential equations, and from the differential equations, a task that can be requested is to find the function whose derivative is this, you see. And it's kind of like, it's the same process, it's the same idea as this antiderivative idea. But these are differential equations, and we're finding general solutions to the differential equation when we go through this process. Well, think about a function whose derivative would be y prime equals 2. Well, it turns out that it would be 2x, but because the derivative of 2x is 2. But let's not forget, when we're going in this direction, to tack on that constant idea. All right, here's another one. Think about a function here whose derivative is 4x cubed. That function turns out to be x to the fourth, you see, because the derivative of x to the fourth is 4x cubed. But let's not forget to tack on the plus c. Okay, so here is a function whose derivative is that. And it is the family of those functions that we're talking about over here. Now, to make the request for antiderivative, we are going to use a certain symbol. And that symbol kind of looks like a tall S. But to ask the question, what is y if the derivative of y with respect to x is f of x? If this is the function that we're starting with, sort of, then what is the antiderivative function? The request is made like this. It's made as y is the integral of f of x dx, and it is that function f, big F, that we talked about earlier, plus c. Now, to understand a little more, to make this flow a little more evenly, we might go to the differential form of this equation. We might write the differential here, and that differential will flow nicely into this. Remember, the differential would be dy equals f of x dx. And now it's kind of like saying undo derivative over here, undo derivative over here. Well, when we undo derivative, it's integral. It's the integral function that we are looking for. Now, the process is called integration. The function is an integral function. So we're going to use that kind of terminology here. This function is called the integrand, and the dx is designating the variable of integration. We are integrating with respect to x here. And this c is called the constant of integration. Now, the process is called antidifferentiation or indefinite integration. Now, it's called indefinite integration for this reason. We're going to find in our investigation that I want to correlate this with finding derivatives. You know, when we were in the derivative world in the last chapter, when we found derivatives, we could be in one of two areas. We could be finding a derivative function, or we could be finding the derivative at a point, the derivative of a function at a point. So in this area of integration, we're going to find integral functions, and which is indefinite integration. And we're also later going to investigate the idea of integration within a certain boundary, and that's definite integration. So what we're talking about here, because we're generating functions, is indefinite integration. All right. There are certain ideas in the process that are similar to the differentiation idea, and because we're already familiar with the differentiation, the integration is going to be particularly easy, I think. Remember, when we're differentiating a constant times a function, we can think of the constant as being the constant times the derivative function. You see, we can kind of draw out the constant. We're going to find that to be true with integration here in a minute. And the derivative of the sum or difference of functions means the derivative of one function plus or minus the derivative of the other. So we can kind of separate the process out in that situation. We're going to find the same to be true with integration. That is, the integral of k times f of x with respect to x dx is k times the integral of f of x dx. And now these are just simplification ideas here, just like these were simplification ideas for derivative. But the integral of the sum or difference of functions with respect to x is the integral of f of x dx plus or minus the integral of g of x dx. It kind of allows us to separate our problem a little bit, just like it did for differentiation, and think slowly or in parts about what we're doing. Now, here are some specific ideas. The integral of 0 dx is simply c, and it is simply c, a constant, because the derivative of the constant is 0. The integral of a constant k with respect to x, or dx, is k times x plus c, and it is because the derivative of the kx plus c will give k. You see, we can always kind of check this idea of integration by performing the task of differentiation. Now, here's the one that really has the power. And I say it has the power. It's even called the power rule. It gives us a great deal of power in what we're doing with this integration idea. It's the integral of x to the n dx is x to the n plus 1 over n plus 1 and then plus c. Now, let's just take it in parts here. We'll notice that what we're doing is we're applying an exponent greater than the exponent that we have here. It's n plus 1. We're dividing by the same n plus 1 that's up there. So it's a rather simple process once we become familiar with it. And we can't forget to tack on that plus c. Now, because we have a divisor here and we have n plus 1, if n takes on the value -1, you notice that the denominator becomes 0 and therefore undefined. So this definition applies for all n except for n equals -1. Now let's take this idea, this power rule idea, and let's apply it over here. Let's slide back over here for a moment and think about this from a mechanical standpoint. If we are going to find the antiderivative of this derivative, then we're taking the integral of this. And in taking the integral, it's kind of like, here's what we're doing. We're taking the integral of 5x to the 4th with respect to x, or dx. Okay, now when we do that, we're thinking about, okay, this is really, and I can use the notion of the 5 times the integral of x to the 4th dx, if I want to think about it like this. Sometimes you'll write this, sometimes you won't. But then with our power rule from over there, this becomes, let's see, 5 on the outside. It is x to an exponent 1 greater than this divided by that same exponent. And now we have, and then plus c. And now we have a nice cancellation here. So it's x to the 5th plus c, and it is x to the 5th plus c that we had here. I suggest you take a look in your textbook at the integration formulas, and you'll find there integration formulas having to do with trig functions. But look at those in your textbook. I could write them up here, but you can look at them just as easily in your text. Consider some of these problems, and I want to think through these with you the way that I would expect you to think through them. The integral of x to the 4th dx is, well, let's see, we're using this power idea, so this becomes x to the 1 number, an exponent that is 1 larger than 4, that's 5, divided by 5, and then plus the constant. And that truly is all there is to that situation. Here we have the integral of 1 over x cubed dx, and it's handy to rewrite before we integrate. And the whole process here of rewriting, then integrating, and then simplifying is very similar to the idea that we considered in the last chapter when we were finding derivatives. You remember it was a rewrite, derivative, and simplify idea. So here we're rewriting, and we would rewrite this then as the integral of x to the -3 dx, and then we integrate, and let's see, 1 larger than this is x to the -2 over the -2, and then plus c. And simplifying, we would get, let's see, it's negative, 2 in the denominator, the negative exponent in the numerator kicks down that base. So this becomes -1 over 2x squared, then plus c. For this next one, we can go through the process. I'm going to show you kind of the long way and then the short way of working this one. Because we're going to need to streamline the process right quick here for our later purposes. Here we could think of this as the 5 as a coefficient here, and 5 times the integral of x squared dx. And then we could say then that this is, now let's integrate here, we would have 5 times x cubed over 3 plus c. And then, multiplying through by 5, we would get, let's see, 5/3 x cubed plus 5c. Now, this 5c, though, the constant here can always be referred to as simply c. We don't have to put a coefficient onto a constant. It's still a constant, you see. So we really would just write this as a c. We wouldn't put the 5c on there. And as a matter of fact, the whole process is streamlined kind of like this. Let's come all the way back to the beginning and not even write the idea that 5 is sort of outside of the integral idea, and consider it like this. We understand that 5 is a coefficient that's just going to be carried along. So it's just 5 and then times, you see 5 times, now integrate here, and we have x cubed over 3, and then plus c. And it streamlines the process quite a bit. So we have then 5/3 x cubed plus c. Similar to what we had before, but a little bit faster. Here we have the integral of 2 sine x dx, and once again we can just let the 2 tag along, say 2 times. Now, the integral of sine x. The integral of sine x. Let's see. The derivative of something is sine x. What is that? Well, it turns out to be negative cosine. So this is 2 then times negative cosine x, because the derivative of negative cosine would be sine, because the derivative of cosine x is negative sine x. So pop that negative in here, and boom, we have the derivative of this is sine x. All right, then of course the plus c, and cleaning this up a little bit, it's negative 2 cosine x plus c. All right, so the idea of, upon occasion, of rewriting and integrating and then simplifying is a pretty good idea. Here we have the integral of this function, and notice that, we're thinking about taking the integral of each of these separately. We could write that down if we want to, but it takes an awful lot of time to say that this expression means the same thing as the integral of this minus the integral, or plus the integral of that, plus the integral of this. You see, in each one with dx and so on. And in that circumstance, if you separate it out like that, you have 3 c's involved, and what are you going to do with those? And you have to consolidate the c's and so forth. It isn't worthwhile to go through all of that process. We just understand that we can take the integral of each of these separately, and we just march through and do that. So this then becomes, let's see, 3 times x to the 5th over 5, you see, and then minus 5 times x cubed over 3 plus 1 times x squared over 2, and then just a general plus c, you see, at the end here. And now it's a matter of marching through and cleaning up. So we have 3/5 x to the 5th minus 5/3 x cubed plus 1/2 x squared, then plus c, and that's all there is to it. Here's another one. This one really does require a rewrite, though. It's the integral of this fraction, and notice the numerator is a binomial, so we're going to divide this square root of x into both parts of the numerator. So we'll rewrite in that fashion. We'll think of this as x over the square root of x, and then 1 over the square root of x, you see, as separate terms in our problem. And now we can simplify here a little bit further. This is x to the 1/2 in the denominator, which becomes x to the negative 1/2 in the numerator. And so x times x to the negative 1/2 is x to the 1/2 for this fraction. And this can be written as x to the negative 1/2. And now we can find the integral of each of these separately rather easily. We have, well, let's see, this is x to an exponent which is 1 larger than this. 1/2 plus 1 is 3/2, and then over 3/2. And then here add 1 to negative 1/2, and we get 1/2, and then in the denominator 1/2, and then plus c, and we're cleaning both of these up. This 3/2 becomes 2/3 as a coefficient, x to the 3/2, and then this becomes 2x to the 1/2 plus c. We could pop in our radicals here. We could use the radical form for these fractional exponents if we want to, but for our purposes this is just fine. Consider this problem. Now that we know some things about integration, suppose we start with the notion that f prime of x is 5x. So f of x, f, the big F of x, is the integral of 5x dx. And that integral is, well, let's see, it's 5 times x squared over 2 plus c, or 5 over 2x squared plus c. Now we understand that this f of x is really a family of functions. That c is a variable, it's a constant, but it varies. It can vary, it can take on different values. So in a graphical form, if c takes on a value like, for example, 0, then the graph looks like this. You see, this is the graph of 5/2 x squared. All right, now if c takes on a different value like +2, let's say, then all the graph would do, the interpretation of the graph, would be that this graph moves up 2 on the coordinate plane. So the graph then would have this kind of like this appearance. You see, and if on the other hand c were -2, then the graph, the basic graph, would move down 2. So we would have something that looks like this. Okay, so depending upon c, the graph could be just about anywhere up and down, but shaped like this, that we would want it to be on the coordinate plane. Now it turns out that if we're given just a little more information, we can identify the value of c specifically, and we can identify the specific graph that applies to it, of course. All right, suppose here that we know we're given that f of 2 is 11. Now, that means that when x takes on the value 2, the vertical distance, or the y component, is 11, or the point 2, 11 is on the graph of whatever c, or whatever one of these functions we're talking about. Well, let's see, which one would it be? For what c would f of 2 be 11? You see, that's what we're really asking ourselves. And we can answer that question just by putting in the value of 2 and 11 into this format. And I've done that over here. We start with the basic function f of x is 5/2 x squared plus c. We can think of it as y equals 5/2 x squared plus c. We know that the ordered pair 2, 11 is on the graph, so we replace x with 2, y with 11, and we'll solve it for c. Let's see, 2 squared is 4. We get a nice cancellation with the 2. 5 times the leftover 2 would be 10, so we find c then to be 1. And now we take this value of c and put back into that general form for f of x, and we find the specific function for f to be this, with the c value of 1, that will allow us to have that point, that f of 2, to be 11 on the graph. Consider this problem. It's very much like the one before. It says find the equation for y, given that y prime is 2 times x minus 1, and the point 32 is on the graph of y. All right, let's first of all find the sort of a general equation for y. Y is the integral of, let's see, it's the integral of 2 times x minus 1. And I'd like to write this in sort of an expanded form because it's just a little easier probably to deal with, I think, in taking the integral. So this would then be 2x minus 2 dx. All right, now the integral, let's see, we have for the integral of this part, it's 2 times x to an exponent 1 larger than this over this, you see, over that same exponent, then minus 2x. We could think about an x and an exponent of 1 and dividing by 1, but it turns out to be minus 2x quite easily. And then the constant idea. Then the 2's go out here, so we have x squared minus 2x plus c. And now we have the idea that the point 32 is on the graph of this, and that allows us to solve for c. If we know that the point 32 is on the graph, then we replace x with 3 and y with 2, and away we go. So we would have 2 equals 3 squared minus 2 times 3 plus c. And there is going to be, let me just pause here and say this very seriously. There's going to be a great deal of temptation to skip steps in the algebraic part of the solution of these problems. And I want you to resist that temptation. I want you to try to demonstrate your problem. If you have the mentality that you're demonstrating the problem for some third party, for somebody that you don't know to look at this and follow what you've done, then you have the right idea about how to display your problem. You'll not skip as many steps that way, and you'll probably write a little neater and so forth. And that comes in really handy as the problems get more and more and more difficult. All right, so here we go. Let's continue with this. I'm simplifying on the right side. I'm going to need to go out to the right here, so it'll be 2 equals 9 minus 6 plus c. So I've got 2 equals 9 minus 6 plus c. You notice how I resisted the temptation to bring these together in that step? I'm a good boy, huh? Okay, so here we have 2 equals 3 plus c. Now subtract 3 on both sides. That's pretty easy. We have negative 1 then equals c. And if c is negative 1, then we take this rather general form right here, and we can replace the c with negative 1. So that'll give us y equals, and here we go, let's see, x squared minus 2x minus 1 as the equation that we're looking for. Here's another one. Pretty much the same idea, but we have a little more to do on this problem. It says solve the differential equation, and the differential equation is this one. Now notice that it's f double prime of x is x squared. And we're given some additional information. We're given f prime of 0 is 6 and f of 0 is 3. This information allows us to identify the value of c at every step along the way. And we really have a 2-step process here and not just a 1-step process. So we're given the value of f double prime. That is, we're given that f double prime function. And we want to find f prime. We also want to find f. F is the ultimate function that we want to identify. Okay, so if f double prime of x is x squared, then f prime of x is the integral of x squared dx. And now, let's see, to integrate, we know that this is x cubed over 3 plus c. And since we know that f prime of 0 is 6, that is, since f prime of 0 equals 6, this becomes, well, let's see, in the f prime function, the x is 0, y is 6. So 6 then equals 0 cubed over 3 plus c, so c then is 6. That means that, let's see, in this expression we have c of 6. So f prime of x is x cubed over 3 plus 6. Now we're ready to come down to or find the f function. The f function then will be the integral of this. So it is f of x is the integral of, and I'm going to write this as 1/3 x cubed plus 6, just for convenience, and I need a dx here. And let's see, the integral is 1/3 times x to the 4th over 4 plus 6x plus c. And I can clean this up just a little bit with an x to the 4th. Well, let me write it like this. I'm going to write it with a distinct coefficient. You know, I can do it a couple of ways, but I think I want to write it as 1/12 x to the 4th plus 6x plus c. And now that's what f of x is all about, but we can identify the value of c because we know that f of 0 is 3. Since f of 0 is 3. Now, it just means that when x is 0, y is 3. So we have here, I mean, we can see through this rather quickly. If x is replaced with 0, these terms go out. So if y is 3, when x is 0, then c is going to be 3. So this implies then that c equals 3 because of the nature of our function. Now, just because f of 0 is 3 in all cases doesn't imply that c is going to be 3. It does in this case because of the nature of the function. Now, if c is 3, we can rewrite this then as f of x is 1/12 x to the 4th plus 6x plus 3 as our f function. We have solved the differential equation. The rate of growth of a population of bacteria is proportional to the square root of t, where p is the population size and t is the time in days, where t is between 0 and 10. That is, the derivative of population with respect to time is equal to k times the square root of t. Now, I'd like to stop right here and spend a couple of minutes talking about where the aspects of this equation come from. Why can we write dp over dt? Why is the problem implying a derivative notion? Well, back at the top of the page where it says the rate of growth of a population. Now remember, in the last chapter we talked about rate as being a derivative idea. And that's why we can think of the derivative of the population is a rate of growth. That's the interpretation of that idea. And then the other part, the k times the square root of t, comes from the notion of proportions implying a constant of proportionality. You may recall from college algebra, for example, that if you say something like A is proportional to B, it implies the existence of a constant of proportionality k such that A is equal to k times B. And that's why we have the k times the square root of t idea here when we're talking about proportion. Okay, let's continue. It says the initial size of the population is 500, and after 1 day the population has grown to 600. Estimate the population after 7 days. Well, we start out with our relationship here. dp over dt is equal to k times the square root of t. And we understand that because of the nature of the way we're setting this up, that this is a derivative idea, that this is really a p prime idea, expression. And what we'd like to do is find the population function so that we can find the population after 7 days. So to do that, we know that the population in terms of time is the integral of k times the square root of t dt. And now we'll rewrite using expressing the radical as t to the 1/2 and then integrate. And this is k times t to the 3/2 over 3/2. And now let's simplify a little bit. The 3/2 in that denominator becomes a 2/3 factor here. So it's 2/3 k times t to the 3/2, and all that's plus c. All right, now notice that we have several variables. We have k, we have t, and we have c. And we'd like to identify the value of k and the value of c. We can do that from various aspects of the problem. One part of the problem says the initial size of the population is 500. Now that means that p of 0 is 500. It's like when no time has elapsed, the initial size, you see, no time has elapsed, we have a population of 500. So p of 0 is 500. That allows us then to make a substitution here, actually a couple of them. 500 then is 2/3 k times 0 to the 3/2 plus c. And that middle term goes out, so we know then that c is 500. Now we can rewrite our equation so that we replace c with 500. And now we'd like to find the value of k. And we can do that from another statement in the problem which said after 1 day the population has grown to 600. Well, that means that p of 1 is 600. When t is replaced with 1, the value of the expression is 600. So we can write then that 600 is 2/3 k times 1 to the 3/2 power. And now we'll evaluate, or we'll solve this for k. You know, 1 to the 3 halves is simply 1, and then subtracting 500 on both sides, we'll find 2/3 k to be equal to 100. Multiplying on both sides by the reciprocal of 2/3, we find k to be 3 halves times 100, or k is 150. Well, now we're set up to replace k with 150 and then answer the question that's posed in the problem. You know, we're trying to find the number of bacteria after 7 days, and we can do that by just replacing into this equation. Now notice that 2/3 times 150 gives that 100 coefficient that we're looking at here. Well, let's see, replacing t with 7, we simply evaluate using the calculator, and we find then that after 7 days there are approximately 2,352 bacteria. Given that acceleration due to gravity is negative 32 feet per second, show that the height above the ground of an object thrown upward from a point s0 feet above the ground with an initial velocity of v0 feet per second is given by the function f of t is negative 16t squared plus v0 t plus s0. Now, it's essential in this problem to realize certain relationships regarding position, velocity, and acceleration. You may recall from the last chapter that if f is a position function, then f prime is a velocity function, and f double prime is an acceleration function. And it turns out in this problem that we're given the acceleration function, and we want to work our way back to the position function. So we're starting with the idea that acceleration, which was given to us as negative 32 feet per second, is this. And so we start out with f double prime of t is negative 32. Now the velocity is going to be f prime of t, and that's the integral of the acceleration function. So it's the integral of negative 32 dt. And integrating, we find this to be negative 32t plus c. Now, we need to make a replacement for c. We need to find a value of c if we can, and part of the problem gives us a hint as to what we need to do. The initial velocity is given to us as v0. Now, initial velocity means the velocity when no time has elapsed, at the very beginning of what's happening here. So the initial velocity, or v0, is really f prime of 0. It's really this velocity function when time is 0. And f prime of 0 means replace that t with 0 and evaluate, and then we find c then to be v0. So if v0 is c, we can rewrite our velocity function like this, as negative 32t plus v0. All right, now we'll turn our attention to the position function, and the position function then is the antiderivative, or the integral of the velocity function. So we want the integral of negative 32t plus v0 dt. And we take each part separately, sort of, and it's negative 32t to an exponent 1 larger than 1, that's 2, and then divide by 2. And then attach the t to the v0, and then add a constant, and we're done. Now the negative 32 and the 2 can cancel, so we get the negative 16 t squared plus v0 t plus c. Now we'd like to do something about the c. We'd like to examine the problem and figure out what we can replace c with. And remember that from our original, here's the original problem, and there's something I want to point out to you here. It says from a point s0 feet above the ground. So the whole problem is starting at this point, this initial point. So kind of like initial velocity, this is an initial position, and it's the position when no time has elapsed. So we can think about the problem like this. We can say that the initial position is s0, and s0 is f of 0. So f of 0 means replace t with 0 in our position function, and evaluate, and the two terms go out leaving C, so C is equal to S naught. And that just means that we replace C with S naught, and here is the position function that we were trying to derive earlier.